You do it every single day, probably without a second thought. Your phone's running low, you grab the charger, plug it into the wall, and boom, it just works. But what if I told you that behind that simple action is this incredible story of transformation, control, and some seriously amazing microscopic engineering? Okay, let's get into it. Because see, that little white block you plug in, it's not just a plug. It's so much more. It's a translator, it's a gatekeeper, and it's a guardian, all wrapped up in one tiny package. It's performing this whole series of super complex steps to take the raw, wild power from the grid and tame it, making it safe and usable for the delicate electronics in your pocket. So let's start our journey right where you do, at the wall outlet. The electricity that's waiting for you there is powerful for sure. But here's the thing. It's not at all what our modern gadgets actually need. In fact, you could say it's completely the wrong kind of power. And that right there is the heart of the whole issue. It's like the power grid is speaking one language, a language designed for long-distance travel, while your phone's battery and all its tiny circuits are speaking a completely different one, a language made for steady, controlled power. If you tried to connect them directly, oh man, that would be a very, very short and, well, let's just say a very destructive conversation. This whole situation introduces us to the two main characters in our story. These are two types of electrical current that have been in this famous feud going all the way back to Tesla and Edison. I'm talking about alternating current, or AC, and direct current, or DC. So alternating current, AC, that's the language of the power grid. And just like its name says, it doesn't flow in one neat direction. Nope, it rapidly alternates back and forth, over and over. Direct current, DC, on the other hand, is the language of your phone's battery and all your electronics. It's simple. It flows in one, steady, constant direction. Just think of it like water flowing nice and smoothly through a pipe. And this right here just lays it all out perfectly. Look on the left, that's AC's signature sine wave. See how it's constantly flipping between positive and negative? It's all over the place. Now look at the right. That's DC. It's just a flat, straight line. It's predictable, it's stable, and it's exactly what all the sensitive little components in your phone are craving. So you might be thinking, okay, if all our devices need DC, why are we even bothering with AC? And that's a great question. The answer is all about efficiency. It's way, way easier to step up AC voltage to super high levels, which lets it travel hundreds of miles across power lines without losing much energy. Then we can step it down to a safe level right before it gets to your house. Pulling off that trick with DC, much, much harder to do. All right, so we've got this problem, right? We have AC power in the wall, but we need DC power for our phones. How in the world do we bridge that gap? Well, the answer lies in this absolutely remarkable class of materials that are, no exaggeration, the foundation of all modern electronics. Let's talk about semiconductors. These things are kind of weird. They're not great at conducting electricity, but they're not great at insulating or blocking it either. They're somewhere in that sweet spot right in the middle, and that's their superpower. It means we can precisely control their conductivity. We can basically tell them exactly when to let electricity flow and when to block it. And we get that control by doing something called doping, where we add these tiny specific impurities into a pure semiconductor like silicon. This creates two new flavors of material. You've got your N-type, which has a bunch of extra free-moving electrons, and then you have P-type, which has a shortage of electrons, creating these things we call holes. You can kind of think of it like creating one material with too many players for the team and another with not enough. But when you put those two together, oh, that's when the magic happens. You get a diode. This is the simplest semiconductor device you can make, but it is absolutely essential. The best way to think of a diode is like a one-way street for electricity, or maybe an electronic check valve. It lets the current flow through in one direction, no problem, but it slams the door shut if it ever tries to go the other way. Here's how it works. When you apply voltage in the correct or forward direction, we call this forward biased. The gate just swings right open. The current flows through super easily. You can see how the electrons in those holes move toward each other and pass right through. But if you flip that voltage around and apply it in the reverse direction, that's reverse bias. The electrons and holes get pulled away from each other, the gate slams shut, and almost no current can get through. It's a dead end. And that one-way behavior? That is exactly what we need to solve our AC problem. This whole process of using a diode's one-way gate to turn AC into DC is called rectification. It's so clever. By putting these diodes in just the right spot, we can take that wavy back and forth AC current and basically just chop off the entire half that's going in the wrong direction. What's left is a bit bumpy, yeah, but it's now flowing in only one direction. We have successfully turned AC into a crude form of DC. Okay, we're getting so much closer now. We've managed to convert the power, but we also need to control it with just incredible precision. And this is where we make a really important leap. We move from the world of the electrical to the world of the electronic. And that difference is huge. See, electrical is all about raw power. It's about generating it with conductors like copper, transmitting it as AC, and using it for simple stuff like light bulbs and heaters. But electronic, that's all about control. It's about information. It uses those special semiconductors. It runs on our nice, clean DC. And it's built from active components that can actually make decisions. And the undisputed hero, the king of the electronic world, is the transistor. The simplest way to think about it is as a microscopic switch with zero moving parts. A tiny little electrical signal can flip the switch on or off, and in doing so, it can control a much, much larger flow of electricity. It's these tiny switches, billions of them working together, that make your phone a supercomputer that fits in your hand. Okay, we have officially met all the key players in our story, so let's put it all together now. Let's trace that entire secret journey of electricity, from the massive power plant all the way into your pocket. So here we go. First, high voltage AC is generated and shot across the country on power lines. Then, that little charger block you have transforms the high voltage from the wall down to a much safer, lower voltage. Next up, our one-way gate friends, the diodes, perform rectification, turning that low voltage AC into low voltage DC. And finally, sophisticated electronic circuits built with billions of transistors manage that DC power, smoothing it all out and feeding it to your battery at the absolute perfect rate. So the next time you plug in your phone, just take a second and remember what's really happening. You've got this invisible force generated miles and miles away that travels all the way to your home, completely changes its fundamental nature from AC to DC inside that little charger, and is then carefully managed by billions of microscopic switches. All of that just to bring your screen to life. It's a truly incredible journey that happens in the blink of an eye.